This is the first learning sequence in block number 2. We are going to talk about how to use information we gained about our sample for describing the whole population. So how to generalize the knowledge about your sample to the whole population, how to find this link between sample and the population. And that's part of statistics we call inferential statistics. We will start with confidence intervals, but let me remind you first what we actually have learned in block number 1. So in block number 1, we found out that when you take a sample from population and, for example, measure particular property of the sample, let's say we talk about height of adult people from particular country, or maybe concentration of chemicals in a particular lake. In this case, these values that you measure or observe, they will be random. And therefore, if you want to get some knowledge about these values, if you want to find some information, what's going on with these values and so on and so forth, you need to describe your sample. You need to describe your values. And that's exactly what we have learned in block number 1. We found out that there are two different approaches to describe random values. One is called non-parametric approach. It's based on ranks. Rank, it's just the position of value. When you order the values, the position of every value in this ordered sequence, it's called rank. And then based on these ranks, you can compute sample quantiles. You can find how many values are smaller than given. And then you can compute the percentage of these values, which we called also relative frequencies. And then you can do some approximation. For example, if you have, let's say, 10 values, you still can approximate and find out, for example, the 5th percentile, the 15th percentile, and so on and so forth. And based on these approximations, you can compute different intervals, like interval of 90% of most common values, interval of 50% of most common values, and many other things. We also learned that we can actually use these quantiles to measure extremeness. We learn how to measure extremeness of your sample based on quartiles, which gives you boundaries for 25% values intervals. And then we compute in IQR, and then we use IQR to measure extremeness, and so on and so forth. But there is one limitation. You need enough number of values in order to use non-parametric approach, because it's based on percentages, right? It's based on the relative frequencies. And strictly speaking, you need 100 of values if you want to make it precise, but at least 20 or 30 values would be a good number to use. Okay, so that's one of the downside of non-parametric approach. On contrast, we also learn a parametric approach. In parametric approach, we assume that there is a theoretical function that describes distribution of these values. And when we say distribution, we first of all mean the densities. So in different parts of range of your values, it's the distance between min and max, you have different densities. So in one part of this range, you have more likely chance to find a value, and that gives you the area with higher density. In some parts, the chance to find a value is small, and that gives you the area or the interval or sub-interval of the smaller density, and so on. And then we also learned that in many cases you have a central tendency, so it means that the values tend to have a highest density in the middle. Okay, so that's what we call a parametric approach. Parametric approach is based on theoretical distributions. So first of all, if you want to use it, you need to find out which distribution to use, and if your experimental data can be fitted by this distribution relatively well. And then you use sample instead of using sample to estimate sample quantiles and then intervals, percentages, and so on and so forth. In this case, we use sample to estimate distribution parameters. And since number of parameters usually is limited, for example, you remember in normal distribution there are 2 parameters, in uniform distribution there are 2 parameters, and so on. Strictly speaking, you don't need that many values. Of course, the more the better, because the estimation will be more precise. That's what we are also going to talk about in block number 2. But in principle, you don't need that many values to estimate these parameters, right? And then intervals, measure extremeness of values, and so on and so forth. They all based on the estimated parameters. So you don't need to reuse your values over and over again. You use your values only once to estimate parameters of your population, of your distribution. Okay. So that's the parametric approach. And parametric approach will be the main approach that we are going to use in block number 2 or 3. And then we will come back to non-parametric approach in block number 4, where we will also talk about inferential statistics for non-parametric approach, how to do this for non-parametric approach. Okay. So we stick to parametric approach for now. And you remember that parametric approach gives us a link between sample and population, And this link is via theoretical distribution. So we use theoretical distribution to make this link. More details coming in the next 3 learning sequences. So let's recall a problem. We are interested in population. Population are all objects that we investigate. For example, it can be all patients that have a particular disease, or every single drop of water in a particular lake if we analyze, for example, contamination in this lake. Population has different parameters if we talk about distribution. And for example, in case of normal distribution, one of the most widely used parameter is average, right? It's mean of your population, which gives you kind of a central point. It gives us the most expected value. The problem is that we usually don't have possibility to work with population, so we take a sample of small size, relatively small size. In my case, I have a sample size of 5. And then we try to generalize. First of all, we try to describe this sample, right? So in this case, because we are interested in mean, I would measure amount of sugar in every apple from the sample. You can see I have 5 values here because my sample size is also 5. And then I can estimate mu by calculating sample mean. So instead of population mean, I compute sample mean, and then I use it as estimate for the population mean, right? So this is the value I got, 9.5 grams per 100 gram of the total mass, or 9.5 weight percent. Now the question is, okay, so if we call it estimate, so it means that we assume that population average is 9.5 grams, right? So that's the way we do it so far, right? But is it true? Is it indeed, can we expect that population average is 9.5? The answer is no. Moreover, we have no idea what population average is so far, because we have no idea how far this value can be from the true population mean. We don't know yet which parameters influence, which characteristics of your sample influence the distance between the sample estimate and the population parameter. And that's exactly what we are going to learn in this learning sequence. The variation of sample statistic, for example, sample mean, around the true population parameter.